This is integral calculus or calculus 2, basic integration, section 1.3, logarithmic formula for integration. In this lesson, I will be discussing more examples of indefinite integrals applying logarithmic formula for integration. Recall the following basic integration formula. Logarithmic formula for integration, or integration leading to a logarithmic function. In the integral of d over u is in quotient form. U is the denominator, which is a function other than a constant, and du is the numerator, which is the differential of the denominator u. If all of these things are satisfied, then the integral of d over u is equal to ln of the absolute value of u plus c, where u is not equal to 0. Example 1.3.8. Evaluate the integral of sine of 2 ln x dx over x multiplied to the sum of 3 plus sine squared of ln x. Solution. Let us express this integral so that this x is in the numerator. So we have 1 over x sine of 2 ln x dx over 3 plus sine squared of ln x. U here is 3 plus sine squared of ln x, which is the denominator. Let's check if this numerator is the differential of this chosen u. So du is equal to derivative of 3 plus sine squared of ln x, then multiplied by dx. So, but what is the derivative of 3? So that is 0. Derivative of sine squared of ln x is 2 sine of ln x cosine of ln x times 1 over x, then multiplied by dx. So that's the differential of u. So applying the identity sine 2 theta is equal to 2 sine theta cosine theta. So this right side is equal to sine of 2 ln x, then times dx over x, which is exactly the numerator. So hence we have du over u. So the integral of this is equal to ln of u. So but u is equal to 3 plus sine squared ln x, which is never negative or 0. So the integral is ln of 3 plus sine squared of ln x plus c. So again, there is no need for the absolute value here because 3 plus sine squared ln x is never negative or 0. Example 1.3.9. Evaluate the integral of r squared hyperbolic cosecant squared of 2r cubed dr all over 4 hyperbolic cotangent of 2r cubed plus 9. Solution. So from this given integral, our u is 4 hyperbolic cotangent of 2r cubed plus 9, which is the denominator. Let's check if the numerator is its differential. The derivative of 4 hyperbolic cotangent of 2r cubed plus 9 is equal to 4 times, for the derivative of hyperbolic cotangent, that is negative hyperbolic cosecant squared, then derivative of 2r cubed is 6r squared, so derivative of 9 is 0, so hence du is equal to 4 times negative 6r squared hyperbolic cosecant squared 2r cubed times dr. So simplifying, we get negative 24r squared hyperbolic cosecant squared 2r cubed dr. But this is not exactly the numerator. So for the numerator to be du, we need this constant factor negative 24. So multiplying by negative 24, that numerator, so we have to balance outside the integral by its reciprocal, which is negative 1 over 24. So this is du over u. So we can apply now integral of du over u. So which is equal to negative 1 over 24 ln of the absolute value of 4 hyperbolic cotangent of 2r cubed plus 9 plus c. Example 1.3.10. Evaluate the integral of tangent 3t dt over 4 plus log of cosine 3t to the base 2. Solution. This integral has the denominator 4 plus log of cosine 3t to the base 2. Let's take that as our u. Let's check if the numerator is its differential. So the derivative of 4 is 0. Derivative of log of cosine 3t to the base 2 is negative 3 sine 3t over cosine 3t ln 2 times dt, so that's du. But sine 3t over cosine 3t is tangent 3t, then times negative 3 over ln 2 times dt, so that's du. So this numerator is not the differential of u, so there is a missing constant factor, negative 3 over ln 2. So let's supply that, negative 3 over ln 2 inside, which is in the numerator, and then balance outside by its reciprocal, negative ln 2 over 3. So this numerator now is the differential of u, and the denominator is the u. Hence, we can apply integral of du over u, giving negative ln 2 over 3 times ln of u, absolute value of u, but u is equal to 4 plus log of cosine 3t to the base 2. So again, the integral is given by negative ln 2 over 3 ln of the absolute value of 4 plus log of cosine 3t to the base 2 plus c. Example 1.3.11. Evaluate the integral of x multiplied to the sum of x and 1 times e to the 2x added to cosine 2x minus tangent x secant squared x quantity dx all over x squared e to the 2x plus sine 2x minus tangent squared x. Solution. So let's take the denominator as u, which is equal to x squared e to the 2x plus sine 2x minus tangent squared x. Its differential is given by, for the first term, the derivative is 2x squared e to the 2x plus 2x e to the 2x. Second term, plus 2 cosine 2x. Third term, negative 2 tangent x secant squared x. Everything multiplied by dx. So let's factor out 2x e to the 2x from the first two terms, giving 2x times x plus 1 times e to the 2x plus 2 cosine 2x minus 2 tangent x secant squared x quantity dx. So here, so there is still a common factor among these three terms. So that is 2. Factoring out 2, we are left with x plus 1 times e to the 2x plus cosine 2x minus tangent x secant squared x quantity dx. So checking the numerator, so this is not du. So there is a missing constant factor 2. So let's supply that 2 inside, which is in the numerator, and then balance outside by 1/2. So numerator now is du, denominator is u, so we can apply integral of du over u, which is equal to ln of the absolute value of u plus c. So getting 1/2 ln of the absolute value of x squared e to the 2x plus sine 2x minus tangent squared x plus c. Example 1.3.12. Evaluate the integral of dy over square root of 1 minus 4y squared multiplied to the difference between sine inverse of 2y and 4. Solution. So let us express this square root of 1 minus 4y squared in terms of its exponential form. So that is 1 minus 4y squared quantity to the 1/2. If we are going to put it up to the numerator, it is 1 minus 4y squared quantity to the negative 1/2, then times dy over sine inverse of 2y minus 4. Let's take u, which is equal to sine inverse 2y minus 4. So du is equal to 2 dy over square root of 1 minus 4y squared. This can be written as 2 times 1 minus 4y squared quantity to the negative 1/2 dy, which is not exactly the numerator. So there is a missing constant factor 2. So let's multiply the numerator by 2 and then balance outside by 1/2. So this is now du, denominator is u. So we can now apply integral of du over u. So getting 1/2 ln of absolute value of sine inverse of 2y minus 4 plus c. Example 1.3.13. Evaluate the integral of cosine 2x dx over e to the sine 2x minus 2. Solution. From this integral of cosine 2x dx over e to the sine 2x minus 2, taking the denominator as our u, impossible for cosine 2x dx to be its du. So the trick here is to multiply both the numerator and denominator by e to the negative sine 2x. So getting e to the negative sine 2x times cosine 2x dx all over 1 minus 2 e to the negative sine 2x. So our u here is 1 minus 2 e to the negative sine 2x. Its du is equal to negative 2 times e to the negative sine 2x. Derivative of negative sine 2x, we have negative cosine 2x, derivative of 2x is 2, then multiplied by dx, so that's du. Simplifying, we get 4 e to the negative sine 2x times cosine 2x dx. Checking the numerator, so this is not exactly the du, so we need a constant factor 4 to complete the du. So we have multiplying by 4, balancing outside by 1/4. So this numerator now is du and the denominator as u. So applying integral of du over u. So we have 1/4 ln of the absolute value of 1 minus 2 e to the negative sine 2x plus c. Example 1.3.14. Evaluate the integral of secant x dx. Solution. This integral does not take the form of du over u. If we're going to bring secant x in the denominator, it will become dx over cosine x. Still, you will not have a differential for the numerator if we take cosine as our u. The trick here is to multiply both the numerator and denominator by secant x plus tangent x. Hence, we have integral of secant squared x plus secant of x tangent x quantity dx all over secant of x plus tangent of x. So let's take secant x plus tangent x as our u, and then du is for the derivative of secant x, that is secant x tangent x, derivative of tangent x, that is secant squared x, then everything multiplied by dx, so that's du. Happens to be exactly the numerator. Hence, we can apply integral of du over u, giving ln of the absolute value of u, but u is secant x plus tangent x, then plus c. Integration of improper rational functions. If the integrand is an improper rational function, perform the indicated division first before carrying out the integration. Example 1.3.15. Evaluate the integral of 2x squared minus 7x minus 15 quantity dx over x plus 2. So this integrand is an improper rational function. So first, let's divide this dividend by this divisor x plus 2. So by synthetic division, we have 2, negative 7, negative 15, taking the opposite of positive 2 as our multiplier here, so which is negative 2. So bring this down, then multiply by negative 2. So negative 4, then add negative 11, multiply by negative 2. So that is 22, add 7. So this 7 is the remainder. And these 2 and negative 11 are the constant coefficients of x and, of course, the constant term in a linear expression. So we have 2x squared minus 7x minus 15 quantity divided by the quantity x plus 2. So we have 2x minus 11 plus 7 over x plus 2. So this integral now is equal to integral of 2x minus 11 plus 7 all over x plus 2 quantity dx. So for the integral of the first term, we have 2x dx, then minus 11 integral of dx plus 7 integral of dx over x plus 2. So for the first integral, we have x squared, then minus 11x plus 7 times, so this is integral of du over u, so we have 7 ln of the absolute value of x plus 2, then plus c. Example 1.3.16. Evaluate the integral of 5x squared minus 8x minus 24 quantity dx all over x minus 2, x minus 3. Again, this is an improper rational function. So let's divide first this dividend by this divisor x minus 3. So getting by synthetic division, we have 5, negative 8, negative 24. Our multiplier here is opposite of negative 3, which is 3. Bring it down, multiply by 3, add. So we have 7 multiplied by 3, 21, add negative 3, which is the remainder. And these are the coefficients in the linear expression. So getting 5x plus 7 minus 3 over x minus 3. So this integral now is equal to integral of 5x plus 7 minus 3 over x minus 3 quantity dx. So for the first integral, we have 5 integral of x dx, then plus 7 integral of dx, minus 3 integral of dx over x minus 3. So for the first integral, we have 5 over 2x squared plus 7x minus 3 of ln of x minus 3. Then absolute value of that plus c. So the integral is 5 halves x squared plus 7x minus 3 times ln of x, absolute value of x minus 3 plus c. Example 1.3.17. Evaluate the integral of 6x cubed plus 11x squared minus 14x plus 1 quantity dx all over 2x plus 1. So again, this is an improper rational function. So let's divide first. So by synthetic division, we have 6, 11, negative 14, 1. So our multiplier here is opposite of negative of 1, which is negative 1. And then we'll have additional row here and having divisor of 2, which is the coefficient of x. Bring down 6, divide by 2, which is 3, times negative 1, negative 3, add, that is 8, divide by 2, 4, times negative 1, negative 4, then add negative 18, then divide by 2, negative 9, multiply by negative 1, so positive 9, then add 10, which is the remainder. And these are the coefficients of a quadratic expression. So we have 3x squared plus 4x minus 9, then plus 10 over 2x plus 1. So this integral now is equal to the integral of 3x squared plus 4x minus 9 plus 10 over 2x plus 1 quantity dx. So integration by term. So we have integral of 3x squared dx plus integral of 4 x dx plus minus 9 integral of dx plus 10 times integral of dx over 2x plus 1. But 10 means 5 times 2. So this 2 is needed because the differential of 2x plus 1 is 2 dx. So hence we have x cubed over 3 times 3. So we just have x cubed plus 4x squared over 2. So we have plus 2x squared minus 9x. Then plus 5 times ln of 2x plus 1 because this is du over u. So the integral is ln of the absolute value of 2x plus 1. Then plus c. Example 1.3.18. Evaluate the integral of 4 sine squared theta minus 17 sine theta minus 19 quantity d theta all over sine theta minus 5 times secant theta. So this is not a rational function the way it is written, but it can be considered a rational function in sine theta. So, and it is improper rational function in sine theta. So let u be equal to sine theta, then du is equal to cosine theta d theta, but cosine theta d theta can be written d theta over secant theta. So expressing this in terms of u, we have 4u squared minus 17u minus 19 quantity this d theta over secant theta is du, and then sine theta minus 5 is u minus 5. So this is now an improper rational function in u. So apply synthetic division. So we have 4, negative 17, negative 19. So opposite of negative 5 is 5, which will serve as our multiplier. So divide by, so bring down 4, multiply by 5, so that is 20, add, so positive 3, multiply by 5, 15, add negative 4. So this is the remainder. These are the coefficients or in the linear expression. So getting 4u plus 3 minus 4 all over u minus 5 or over u minus 5. So hence we have this integral now is equal to, in terms of u, we have integral of 4u plus 3 minus 4 over u minus 5 quantity du. So integrating term by term, we have integral of 4u du plus 3 integral of du minus 4 integral of du over u minus 5. So we have 2u squared plus 3u, so minus 4 ln of the absolute value of u minus 5, then plus c, where u is equal to sine theta. So in terms of sine theta, so this is equal to 2 sine squared theta plus 3 sine theta minus 4 ln of sine theta minus 5, absolute value of this, then plus c. Example 1.3.9. Evaluate the integral of 7 ln squared y plus 22 ln y plus 3 all over y times ln y plus 4y quantity dy. So this is an improper rational function in ln y. So let u be equal to ln y. So its du is dy over y. So let us express this in terms of u. So we have 7u squared plus 22u plus 3 quantity du all over u plus 4. So dy over y here is du. So by synthetic division, we have 7, 22, 3, and then our multiplier here is opposite 4, which is negative 4. So bring down 7, multiplied by negative 4, we have negative 28. Add negative 6, multiply by negative 4, positive 24, add 27. So we get 7u minus 6 plus 7 plus 27 over u plus 4. So this integral is equal to integral of 7u minus 6 plus 27 over u plus 4 quantity du. So let's integrate this term by term. So we have 7 integral of u du minus 6 integral of du plus 27 integral of du over u plus 4. So we have for the first integral 7 over 2u squared, then second integral negative 6u plus third integral 27 ln of u plus 4, then absolute value of that plus c. So but u is equal to ln y, so hence we have 7 halves ln squared y minus 6 ln y plus 27 ln of y plus 4, then plus c. So that's all for now. So thank you for watching. Please don't forget to subscribe to my YouTube channel, Usano-Goldie RL Marquez. Bye.